and welcome to the last lecture on the brief tour of the universe, where we're going to end up right back here in the Cape, actually. And so tonight's lecture is entitled From Meerkat to the SKA. And so what I'm going to try and end off with is a little taste of radio astronomy, what sort of objects and processes radio astronomers study, and then take you towards the SKA, the Square Kilometre Array, which will be the most ginormous telescope ever built on the surface of the Earth, and our contribution to that project, the Meerkat Radio Telescope. So just to put, again, things in more context, radio astronomy is actually a very new field of astronomy. It only began back in the 1930s. Carl Jansky was an engineer working for Bell Labs in the USA, and he was tasked with trying to understand sources of interference for shortwave radio communications. And this was his big antenna that he was partly responsible for building. And what he was doing was studying shortwave radio interference, and by mistake, he discovered radio emission from the center of the Milky Way. Until then, nobody had realized that you would get radio emission from space, necessarily, and so this was a really exciting discovery. In honor of Carl Jansky, we have a unit which we call the Jansky, which is the units of flux density that we measure for radio sources. Typically, they're faint sources, and so we talk about them in this convenient unit. Now, if you compare that the first optical telescope used for astronomy was put together by Galileo in the early 1600s, optical astronomy was pretty solidly established, but radio astronomy only starting in 1930. It's less than 100 years old. Now, people were very excited by this discovery at the time, but it was unfortunately the time of the Great Depression. There was a radio engineer named Grote Reber who was very excited and wanted to follow up on this discovery. He was also a ham radio operator. Here he is. And he started applying for jobs. He wanted to work at Bell Labs, in fact, and study this in more detail. But unfortunately, because of the budgetary constraints of the time, they were not hiring, and nobody was hiring new astronomers. So he decided, well, to hell with that, I'm going to build my own telescope then. And he did, in his backyard. So he built his own radio antenna. Here's the feed, the receiver, here's the reflecting dish. And he mapped out the Milky Way, and he found emission from other sources in the sky in the direction of the constellation of Cassiopeia and of Cygnus. And he had actually, he studied the radio sky for the rest of his life. He moved to Hawaii, he also moved to Tasmania, and this was his big thing. Now, since then, after the Second World War, radio astronomy, thanks to the technological advances of radar, etc., it made some progress, and the money started coming in, and people could start using it as a real part of astronomy. And since then, we've built many telescopes on the surface of the Earth. The Parkes Radio Telescope is one of these. It's a 64-meter telescope near Sydney, and so it's a 64-meter diameter, and it has this is where the astronomer will sit, over here. And it's famous for being used to track the Apollo 11 signal, the TV signal. And so if anybody's seen that movie, The Dish, this was the Parkes Radio Telescope that features heavily in that movie with Sam Neill. So not only can it track astronomical signals from space, but also human ones. Another very large telescope, the biggest steerable radio telescope we have on the Earth, is the Green Bank telescope that I showed you, I think, on the first lecture, and it's 105 meters in diameter. And it's got this special Gregorian offset design so that it can maximize the collecting area. The other, almost exactly the same size, there's the Effelsberg telescope in Bonn in Germany, and it's also steerable. Here you can see it compared to the size of a car. and so very similar. Now, recently, only recently demoted to second largest telescope in the world, is the Arecibo telescope. This telescope is based in Puerto Rico. It's nestled in the mountains. It's not a steerable radio telescope. It's 300 meters in diameter, or 20 acres of area. And it's a very, very sensitive instrument. And it's famous from being in that James Bond movie, GoldenEye. And I think they were running around up here somewhere in the detector. It can't be steered to track a source as the Earth rotates, but the detector can move a little bit along these cables. Otherwise, it relies on the rotation of the Earth to be able to scan the sky. It was originally constructed actually with a mesh, like a chicken wire surface, but then in the 1970s, it was built in the 1960s, but in the 1970s they resurfaced it with thin metal panels, and that allows it to observe slightly higher frequency radiation. So the winner for the largest radio telescope on Earth at the moment is the FAST telescope, where FAST, F-A-S-T, stands for the 500-meter spherical aperture telescope. This telescope came online at the end of last year. It's in China, and it's got a similar idea to Arecibo. It's also a fixed, enormous dish, half a kilometer from this side to that side. And we're looking forward to seeing what amazing observations are going to start coming out of this telescope. In fact, I'm going to a meeting in India in a couple of weeks' time, where there will be some astronomers coming from China, and we're hoping that they'll be able to give us some fresh new information about what's happening there. So you'll have noticed that radio telescopes are huge. And so why are they so enormous? Well, typically, radio sources are faint, and radio telescopes have to be built as big as possible to collect as much light as possible. So we saw this picture on Monday where we were looking at the buckets. You can think of your telescope as your light bucket, and if you've only got a limited amount of time to collect light, then you want to build your bucket as big as you can. But the other reason is that we need large sizes or apertures to resolve small angular scales on the sky. And this is because of what is called diffraction. Now, when I'm talking about resolving small angular scales, this is what I mean. What we want to be able to do is separate two objects which are close together on the sky and actually be able to see them as separate blobs rather than all merged together and fuzzy and blurry in our images. So this is a nice illustration of what I mean. So in these are both images of the Andromeda Galaxy. This one is at a 5 arcsecond resolution, and this one has a 1 arcsecond resolution. And so in this image, we can see as separate two objects which are separated by an angular distance of 5 arcseconds, whereas in this picture, it's much sharper. We can separate objects that are as close as 1 arcsecond in the image. And you can just see straight away the better resolution. And now, as I alluded to, resolution is limited by this phenomenon called diffraction that you can't escape. And what happens with diffraction is that as a wave passes through an opening, it is bent. And so what happens here is you've got a wave coming in. Imagine you've got a wall, you've got a little opening in your wall. As the wave passes through that opening, the rays are spread out instead of being parallel anymore. And the longer the wavelength, the more this happens. But luckily, you can counteract that by making a bigger opening, because the larger the opening, the less it happens. Now, because radio wavelengths are long wavelengths, much longer than the wavelengths of light, when we talk about the wavelengths of radio waves, we're talking about centimeters and meters. You can actually see these things. When we're talking about optical wavelengths, we're talking about hundreds of nanometers, 10 to the minus 9. That means a 0,9 zeros and then your number. And so because of these longer wavelengths, we need to build even larger detectors to allow us to have decent resolution. So you've seen how we get around this poor resolution issue. We build really big detectors, but even the largest single dish detectors are quite limited in the resolution that we can get. So we have to get around this problem another way. And so what we do is we build an antenna array. So we build a whole lot of radio telescopes in an array, and we put the signal from each of them together. We call this interferometry. So in interferometry, what we do is we take the signals from our individual antennae, and we basically look at the interference pattern created between what we receive from each pair of antennas. And we put these signals together in a computer, we combine them, we Fourier transform them for the engineers, and we build up an image. So you can substitute an antenna array for a single large telescope. And now your resolving power is related to the longest distance between any two of your antennae. So if you can build, let me give you an idea. So if you had a single dish that was 5 kilometers in diameter, it would give you the same resolution as two smaller dishes, which are separated by a distance of 5 kilometers. Now, obviously, your big dish, which is 5 kilometers in diameter, will be more sensitive because it has an enormous reflector and it can collect a lot of light compared to two smaller ones. But then you just build a whole lot of small ones so that their combined collecting area adds up to a large number. So here I want to just illustrate this. So here's the GBT, a single large telescope. It's incredibly sensitive with this amazing collecting area, but it can only observe small patches of the sky at a time. Its resolution and its field of view, the area on the sky that it can look at in one pointing, is limited by the wavelengths that you're observing and inversely proportional to its diameter, its aperture. So if I plug into this little formula over here, the wavelengths of 21 centimeters, which is the wavelengths emitted by neutral atomic hydrogen in the universe, then I would be able to observe a patch of sky that's only 0.15 degrees across. And to give you an idea of that sort of size, if that's the full moon, which spans an angular size of about half a degree, then this is the size of the patch of sky that one pointing of the GBT would see. So if you wanted to build up a picture of an object that's quite big, you're going to have to point that big telescope a number of times and then put all those pictures together so that you can build up a picture of the whole object that you're wanting to look at. However, if you put your telescopes, your smaller antennas, in an array, you can get pretty good sensitivity. If you build enough of them, then all their collecting areas add up. But the advantage of this is that they have a big field of view. In other words, they can see a lot of the sky at once. And they can have a high resolution. So in this case, when you have an array, then you would calculate the field of view, the patch of sky that you can see, where this diameter that you're dividing by is the diameter of a single small dish. And so obviously the smaller this D gets, the bigger the piece of sky you can see at once. So for the very large array in New Mexico, the diameter of one of these dishes is 25 meters. So think of a 25-meter swimming pool. And that gives you a size on the sky which is bigger than the full moon with this array, because we just look at how much one of these little dishes can see at once. But the resolution that you can get is dependent on the longest distance between any of those two antennae. And the VLA, the Very Large Array, the longest baseline is of the order of 30 kilometers. And so you can get much higher resolution with this telescope than you can with the giant Green Bank telescope, the GBT. So these are the pros of observing with an array. And so here, just to put everything in perspective, the sensitivity of this array, there are 27 of these 25-meter dishes. It would have the sensitivity of a single dish with 130 meters diameter, but much higher resolution. So there are a number of interferometers or arrays on the surface of the Earth. Probably the most famous one is the Jansky Very Large Array, which is, as I said, 27 25-meter antennas. And they're actually on tracks. So what they do is they can move the antennas with respect to each other. And so what they do is they actually have, I think, 4 or 5 different setups where they spread them very, very far apart, or they pack them closer together. And they've got 4 different settings for this, because different astronomers want to measure different things. So if you have quite a bright object that you want to look at high resolution, then you ask for time when the array is spread out at its longest distances, because it's you're worrying about resolution. If you're trying to look at an object that's quite faint, then you want to bring your dishes quite close together to maximize your sensitivity. So this is the power of an array, is that you can get the sensitivity and the resolution. Another large interferometer is the GMRT, the Giant Meter Wave Radio Telescope. 30 of these 45-meter antennas. I think I showed a picture of one of these on Monday. And the surface of this antenna is not solid. It's actually a mesh, a thin mesh. And this is because this telescope is designed to measure quite low-frequency radio radiation, or longer wavelengths than the VLA. And so the surface of the reflector doesn't have to be as smooth as the VLA antennas. Another famous interferometer is the Westerbork radio telescope interferometer in the Netherlands. This one's quite interesting. It's all the 14 25-meter antennas are lined up in a straight line that is exactly east-west, and then they use the rotation of the Earth to map out phase space when they're observing. And then another one is the Australian Telescope Compact Array, ATCA, and this one has 6 22-meter antennas. So that's that one at sunset. So I've shown you a whole lot of hardware. What on earth do astronomers do with these things? Well, we study all sorts of things with our telescopes, and one of the most famous objects that you would study with a radio telescope are pulsars. So we were talking about pulsars as one of the stellar remnants that is left behind after a massive star goes supernova. You might be left at the end with what's called a neutron star, this ball of very compact neutrons, about 10 kilometers in radius, spinning very fast and with very high gravity, because the matter is incredibly dense. This was where you were trying to squash Mount Everest into a thimble. And this is just showing you over here, the signal from a pulsar is picked up by a radio telescope. So this is time, and this is the intensity of the radiation. And you can see that there are regular spikes as the pulsar beams its radiation in our direction, because it's spinning, and the radiation is being beamed along the magnetic axis of the star, which is not lined up with its rotation axis. We get that lighthouse effect, and we get our regular blips. They're not all exactly the same height, but they are very regularly timed, and in fact we call pulsars the best clocks in the universe. Astronomers know how to model exactly when the next pulse is coming, so they're incredibly accurate clocks. I'm going to show you now actually what, if you could convert this signal into a sound wave in terms of just so that your ears can hear how fast these things pulse. This is what it would sound like. I just want to remind everybody that, of course, this is electromagnetic light radiation that we're picking up. I'm just converting it into sound so that you can more easily hear the flashes. Okay, so this is what this pulsar called PSR B0329 plus 54 would sound like. Now, every one of those little ticks is when the neutron star spins once. This is what the Vela pulsar sounds like. And I always find that completely amazing. Imagine this ball of neutrons 10 kilometers across, spinning like this. I'd love to be able to fly up to one of those things and see what it looks like. So I don't know if the animation worked here, but I can just play it again quickly. So this is just to illustrate the red sort of funny shape is the neutron star, and it's spinning, and when that flash comes towards us, that's what we pick up in our radio telescope. Another thing, so radio telescopes are used a lot to look at pulsars. Other things that people are very interested in studying is galaxies. Now, this is a galaxy called Centaurus A, and as you'll know now from our galaxy talk yesterday, this is an elliptical galaxy. It's a bit of a weird elliptical galaxy because the first thing you notice is, what's that stuff in it? Now, typically elliptical galaxies do not have a lot of dust, but this one does. And what we think probably happened to it is that it collided with a spiral galaxy at some point and ate it up. And that spiral galaxy's material became part of this elliptical galaxy. Typically, spiral galaxies have a lot of dust in them, and so this is what we think probably happened here. Now, this is what it looks like in the optical part of the spectrum. So if we were to look at this galaxy through an optical telescope, this is the sort of image that you would see. Now, if I were to use an interferometer to look at this galaxy, that's what I would see. I wouldn't see the background optical image. I would see this false color picture where the galaxy looks very, very different. It looks like there's a tiny blob in the center with these long collimated jets of material ending in enormous lobes which are glowing with radio radiation. To give you an idea of the size of this thing, the radio lobes are 10 times bigger than the Milky Way. That's how far out in space these things extend. They're ginormous. What's happening here is that jets of material seem to be ejected from the nucleus of this galaxy. If we look at the Doppler information, then we can try to extrapolate backwards and figure out how long ago they must have been ejected. And so we get a timescale of about 100 million years. So this structure over here is about 100 million years old. That's much younger than the rest of the galaxy, which will be billions of years old. So this is a relatively recent event in this galaxy's history. Also, just to point out, of course, because we can't see in the radio part of the spectrum with our eyes, when we make an image, what this is showing you is false color, where the red is showing you the brightest part and the blue is showing you the faintest part. So they just make a fake image telling you where the intensity of the radiation is the highest compared to where it's the lowest. So Centaurus A is by no means the only radio galaxy in the sky. There are many of these things. This is another one called Cygnus A, with, again, ginormous lobes of material emitting radio radiation, a little node in the middle at the nucleus of the galaxy, and then you can see over here these very collimated, these very straight jets, where the material is being literally shot out or ejected at very high speed along a very straight line, and then it's billowing out later on. Now, if you zoom in, sorry, this is the radio image. This is another image in the radio. The false color is just done slightly differently. And then if you zoom in on the central nucleus, this is what you see in the visible part of the spectrum. So this is really where the power of multi-wavelength astronomy comes into play. This is why we want to look at things in more than one wavelength. If we had only looked at some of these objects in the optical, we would have missed all this unbelievable structure that's sitting there. When we look at the center, we see a sort of two blobby kind of center. It's very technical. But what we think is probably happening here is that two galaxies have collided, and this maybe is what's giving rise to this amazing jet and radio emission. So what is actually giving rise to the radio emission is that you're having highly energetic charged particles accelerating and releasing radio wavelengths. If we were to look at Centaurus A, this guy, in the sky, imagine we had radio eyes, not optical eyes, and our eyes were tuned to the radio part of the spectrum, and we could see it in the night sky. That's what it would look like. It is huge. It takes up an enormous angular size on the sky. This is the Australian compact array in the foreground. And also, just to point out, this is a beautiful image. It was one of the NASA astronomy pictures of the day a few years ago. Every blob in the background of this image is not a star. It's a radio source in the sky. So this is a radio picture. So everything that's glowing over here, well, this is the moon, everything else that's glowing over here is actually a radio source. So it might be a distant galaxy, it might be a quasar, it might be something else. Now you might ask, what on earth is giving rise to this these lobes of radio radiation, these jets of material? What we think is going on in radio galaxies is that they are what we call active galactic nuclei. So what's happening is that there is a supermassive black hole at the center of these galaxies that is accreting matter. And the gas clouds, stars, whatever's close by, and what's getting affected by its gravity and it's falling in. Now, in the accretion disk, the matter is rotating at high speed. There are magnetic fields in this area around the black hole. And what's happening here is that particles are being somehow ejected along the magnetic field lines. As the charged particles spiral around the magnetic field lines, they release radio radiation. And so these huge structures are caused by the central black holes of these galaxies. The light is, of course, the radio radiation is not coming from the black hole, but the particles that are in the accretion disk and around it, and the particles that are being ejected from this area around it. The exact processes for how jets are made are under intense theoretical investigation. Many people are trying to work out the exact mechanism of how you manage to actually accelerate particles at this kind of angle out of the galaxy. And so I won't be able to answer your detailed questions about that because we're still trying to figure it out. Another thing that radio astronomers study is especially extragalactic astronomers, is the distribution of the elements and the molecules in the universe. So obviously stars are formed in the giant molecular clouds and the nebulae where the temperatures are quite low. And if you want to find out about what's in those molecular clouds, you want to be able to study what their components are, then this is a very useful way to do that. You can learn about atoms and molecules in these gas clouds and in galaxies themselves by looking at the radiation that is emitted by them. So one of the famous emission lines in radio astronomy is the neutral atomic hydrogen hyperfine transition. So let me just show you here. You can imagine this is a very simple picture of a hydrogen atom. This is the proton and this is the electron. And these, most of the time, the proton and the electron have their spins. They're spinning. You can think of it as a quantum number as well. Their spins are in the same direction. But every now and then, what can happen is in the ground state, the electron can flip its spin into the opposite direction. And that gives it a slightly lower energy. And so to jump down to a slightly lower energy level, it has to release some energy, and that energy is released as radio radiation with the wavelengths of 21 centimeters, or a frequency of 1420 megahertz. Now, the probability that this happens is a very small probability. If you were to watch one hydrogen atom and wait for it to do this, you'd have to wait about 12 million years. But luckily, hydrogen is the most abundant element in the universe. There's millions of billions of trillions of atoms in any gas cloud, really. And so many of them are undergoing this flip at any time. And so the signal is actually able to be detected, even though it's weak. And this is a signal that when we are looking at the gas in distant galaxies, it's a very important signal to look for, because neutral atomic hydrogen is the reservoir that forms the molecular hydrogen, which then is the starting point for star formation. And so if we want to understand how galaxies evolve and how stars form, you really need to have a good idea of what's going on in the gas in the galaxy. The other thing about neutral hydrogen gas, especially in star-forming galaxies and spiral disk galaxies, is that the gas extends out further than the stars. We were talking about this when we were talking about how dark matter was discovered yesterday. And so if galaxies start to interact with each other gravitationally, if they start getting close together, the first thing that gets affected is the gas. So I like to show this picture, which this is the galaxy Messier 81 and its two companions. And when you look at this in the optical, these galaxies look, I mean, they're nearby to each other, but you wouldn't think anything particular about them. They don't really look like they're interacting. But when you look in the radio part of the spectrum, if you look at the neutral hydrogen, what it's doing, you can see that they are having quite a serious interaction. They are dragging gas out of each other. They're creating tidal tails. So they're having quite an argument, actually. And this is what we can learn when we look at this long wavelength. People have studied nearby galaxies in a lot of detail, their neutral hydrogen, or what we call H1. And this is a very a famous galaxy survey that was completed within the last 10 years or so now, called THINGS, which stands for the H1 Nearby Galaxy Survey, another acronym. And what they did was they surveyed about 34 nearby galaxies with the Very Large Array, and they made images of these galaxies, the gas in these galaxies. Now, for scale, this is the Milky Way. Now, obviously, this is not their measurements. This is just the size of the Milky Way. So what they did was they looked at a huge range of galaxies in terms of their sizes. They went right from dwarfs all the way out to very large spiral galaxies. So they could sample a nice range of different kinds and try to understand star formation and the role of the gas in these galaxies. They also made these wonderful images because they went and looked at other wavelengths of light, and they put images together to make composites. These are 4 of the THINGS galaxies, where the neutral atomic hydrogen is being shown in the pale blue. The old stars, which are represented by the infrared radiation, is shown in red. And the star-forming regions in the galaxy are shown by ultraviolet in purple. And so this is a beautiful way to really build up the different components of a galaxy by looking at what it looks like in the different wavelengths. And then you can learn about where star formation is happening, how far out does the gas go compared to the stars. And it's quite amazing, actually, how different they are from each other as well. This one has an old stellar population in its bulge, whereas this one does not seem to have the same sort of thing. And so being able to compare galaxies like this helps us build up a picture of their evolution and what sort of processes must be involved in how galaxies age. Now, the other useful thing about a radio telescope, which is an interferometer, is that it delivers data in 3 dimensions. Now, with an optical telescope, usually what you'll do is you'll either have to go and make an image by using the camera on the telescope, or you will decide to take a spectrum of an object, and then the light needs to go through the spectrograph. It's not often that you could do these things at the same time. It's becoming a little bit more common with very special instruments, but it's not a usual thing. But with radio interferometers, the data comes out with 3 dimensions, naturally. You measure you are observing a patch of sky, so you're naturally getting your spatial information, but not only that, you're measuring over a range of frequencies as well, and so you get the spectral axis at the same time. Now, it doesn't just come off magically off the telescope. You actually have to do quite a lot of work to process the data. You Fourier transform it, you clean it up, and then you can get it into this nice data cube form. But once it's in that form, it's incredibly versatile. You can do a lot with it. So what you could do is you could extract all the information just as a function of frequency, and you can get a spectrum. And so these are just like the spectra that I was showing you from the optical part of the spectrum. Here's intensity, and that's frequency. And this spectral line looks a bit funny. It's got 2 peaks. It's called a double horn profile. And this is a typical neutral hydrogen line from a rotating spiral galaxy. And why it's got a double horn is that if one side of the galaxy is rotating, then at any time one side of the galaxy will be coming towards you. And so what will have happened to the light? What kind of shift will it have? It'll have a blue shift. But the other side of the galaxy, which is moving away from you, will be showing you a red shift. In the middle of the galaxies, there's less hydrogen, neutral hydrogen, as you'll have seen. Let's go back, look here. There's not that much blue in the middle. Spiral galaxies don't seem to have a lot of hydrogen in the middle, so they have a bit less there. So this is what you are seeing over here. So you're seeing in this line, spectral line, some of the neutral hydrogen coming towards you, some away from you, the dip in the middle, and that tells you an amazing amount of information. How wide this line is tells you how fast the galaxy is turning. And if you sum up all the intensity of the light that's underneath this profile, you can actually get an estimate of the mass of hydrogen in that galaxy as well. So these are these spectra are incredibly powerful. We can learn a huge amount of about galaxies just by looking at the spectrum, let alone by also being able to look at the image itself. Right. So that's what we can do with current radio telescopes. We are typically, especially in this kind of science, H1 astronomy, limited very much to the local universe. Our current radio telescopes are just not powerful, they're not sensitive enough to be able to measure very deep into the universe. We know very much less about the universe, about the H1 in galaxies far away than we do about their starlight. It's quite easy to measure distant starlight. You saw yesterday with the Hubble extremely deep field that you can measure and observe galaxies that are billions and billions of light years away. But you can't do quite the same with our current radio telescopes because they're just not sensitive enough. So this is part of the motivation for this upcoming monster telescope, the Square Kilometre Array. It will be the biggest, most sensitive telescope ever to be built, up to its build. And it's quite an expensive venture. It's already cost 130 million euros to design it. And it will soon be moving into the construction phase, probably 2018, 2019, and the construction phase has been allocated for the first phase 650 million euros. And these are the member countries, so New Zealand, Canada, China, Germany, India, Italy, Australia, South Africa, Sweden, the Netherlands, and the UK. These are the countries that are putting money together to build this unbelievable instrument. And then shown over here are some of the, they are all of the African partner countries who will host dishes in their countries and who will be part of the SKA, but who are not at this point contributing large amounts of money towards it. And this is where I'd like to show just a quick video, which I think is great to just put the SKA in perspective. Just a couple of minutes long.
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったかな?
¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answer to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
We're building what will be the largest science facility ever built by mankind.
To be able to achieve the scientific goals that we want it to be able to achieve, we need to create a machine which is less telescope. It's almost more an IT machine.
We're pushing technology to its limits.
What we're talking about now is 2 telescopes.
Our site is in the middle of the Western Australian desert.
Far away from towns, radio interference, anything that could impact on the science that we're trying to do. We've already started. We've got antennas at the site. We'll have hundreds of thousands more. It'll stretch out beyond the horizon.
We're building hundreds of dishes in a remote location in the middle of South Africa. And it's really tough. It's a hot environment, it's a dry environment. These dishes are going to spread out over literally hundreds of kilometers.
Een project als dit kan alleen tot stand komen als wetenschappers wereldwijd met elkaar samenwerken.
We've got to get 500 engineers to work together over 20 countries in all the time zones in the world.
It's like building a jigsaw puzzle, but the pieces keep changing.
Part A being designed in one place fits to part B being designed literally on the other side of the world.
Every new telescope, there are always new discoveries, and they are never the discoveries you build a telescope for.
We're almost bound to discover something new, something that will disrupt our current everyday life.
That generates new knowledge now.
Huge amounts of data.
Imagine the amount of data that's flowing through the internet at any one moment. We're talking about that kind of level coming out steadily.
इतनी सारी डेटा का सही मतलब निकालने के लिए नया सॉफ्टवेयर बनाना ही पड़ेगा.
The SKA can do for interplanetary exploration what broadband did for the internet.
We're doing this now. There's equipment on the ground in South Africa and Australia.
Radio waves gives us a unique way of probing the deep universe.
We can do all of this by picking up incredibly faint signals, radio waves coming from the dawn of the universe.
What we will discover is the unknown.
We're going to build the real thing. It's not just dreaming.
Exciting times. So it's an enormous project, and I really like that video for putting that in perspective. So there are going to be 2 sites for the Square Kilometre Array. Both South Africa and Australia were chosen to host it. And what they will do is they will divide up the kinds of antennas. So the very low frequency sparse, what we call sparse aperture arrays, are the ones that they were referring to as already being on the ground in Australia. These will measure the very low frequency radiation. Then these are the mid-frequency aperture arrays. These are something that will only come in a second phase of SKA. In fact, exactly how to design these and make them is still actually up for debate. So people are working intensely. This is an R&D project at the moment. And then the higher frequencies, mid to higher frequency dishes, these will mainly be located in South Africa. So Australia has a smaller array called the ASCAP, the Australian SKA Pathfinder Telescope, and South Africa, as part of our bid to host the SKA, said that we would build the Karoo Array telescope, which I'll talk about in a second. First of all, I just want to quickly show you how the SKA will be better than our current telescopes. So it will be it will give incredibly high resolution. Its survey speed will be much higher than our current telescopes, and it will have a great field of view, so it will be fast, and the sensitivity will be unbelievable. And so these are the 3 areas that you want to be building your new telescope. So as I said, the sites were split, and South Africa is putting the SKA that will be built here in the Northern Cape, which is the very lowest population density in the country. There's some farms and lots of sheep, but not very many people. And the reason for this is that, the reason that we want to put a radio telescope there, of course, is to minimize the radio frequency interference. Cell phones, cars, televisions, microwaves, all those things contribute interference at radio frequencies, and we don't want that to get into our telescope and mess up our data. So this is the Central Astronomy Advantage area, where the core of the meerkat will be located in the Northern Cape. And that's just a sort of rough idea. Here is where the dishes will be in phase 2 when they spread out to our African partner countries. Now, South Africa, as part of our bid, was put forward that we would build a prototype, and our prototype was called the Karoo Array Telescope, and then more money was given to it, and so it was called the Karoo Array Telescope, or the meerkat, and that's where the name comes from. It wasn't actually named after the animal. This is what the meerkat site looks like at the moment. So this building over here is the Karoo Array processor building. It's a very cool building. Most of it's underground, actually, and this is to shield the computers, which will be doing a lot of which will be correlating the signals from the dishes. You obviously don't want any of that radiation to leak out into the telescope, so you want to keep it underground. There are also all these chimneys, vents, and that's because you also have electricity generators down there, and they need to be cooled off. This big building over here is the dish shed, where they construct the antennas, and this is what it looks like inside. So here they're putting together the different struts of one of the antennas. They're 13.5 meters in diameter, and once you construct a dish, then you put it on the back of a truck, and you drive very slowly, and then you put it on its pedestal with a big crane. So there's the first, I think this was the first dish being put on its pedestal by a large movable crane. I think lots of people were holding their breath. And that's what the finished product looks like. Absolutely stunning. And just like the GBT, it has a Gregorian offset. So we have a more open face to collect radiation, and then the receivers are at the end of this arm structure. This is an aerial view of the meerkat site. And you can see, this is a little bit old. There are now more than 20 dishes up. So this was taken a few months ago, but you can see that their pads are already prepared for them, and then the first thing that'll go on is the pedestal, and then they'll build each actual reflector in the shed and then bring it individually to its pedestal, and then they will start to commission that dish. So it's a really enormous engineering project. The amazing thing about the meerkat is that it is delivering much higher sensitivities than the original design actually spec'd. They have done such a good job. They have delivered much better than they thought they even could. And that's actually going to have an impact on the science, an enormous positive impact on the science that we can do with this machine. So there was huge excitement last July because the meerkat, with 16 antennas, all observing a patch of sky together, produced its first light image. So this is a radio continuum image of a patch of the southern sky. And all these little dots are radio sources. Here they've zoomed in on some of them, and you can see here a lovely radio galaxy with its bright nucleus and its radio lobes, and here's another one. So it's the astronomers who are involved in the project at the Meerkat office did an amazing job of putting this together. This is a small fraction of that image. It's 10% of the area of the first one. They've just zoomed in here. And this is also rather lovely in that previously in this patch of sky, only the sources with the purple circles around them were actually known of before. All the other blobs, all these other radio sources that are in this image, no one had ever seen before. And so more than 200 sources are being seen in this image, in fact, where before we only knew of 5. So meerkats are already starting to make a real impact. Now, the project planners, back in 2009, put out a call for proposals. I mean, this has been a long project in the process. And of course, when they started to build it, they wanted to know what the astronomy community, not only in the country but in the world, wanted to do with a machine like this. And so they put out a call for proposals for people anywhere in the world to ask for time on the telescope to do a large survey, a survey that would take more than 1,000 hours of time, and to tell them what they would use that time to do. And about 20 large proposals were submitted by international teams, and they chose 10 of them. And as it turns out, 4 out of these 10 actually are led by astronomers at UCT. And those are the Laduma project, the Mongoose, the Mighty, and the Thundercat. Again, our acronyms. And I'm going to tell you two more minutes just what they are. So I'm going to start with my favorite one because it's the one I'm co-leading with 2 colleagues from America. And we call this Laduma, or Looking at the Distant Universe with the Meerkat Array. And what we plan to do is stare at one patch of sky for 3,000 hours, sort of like the Hubble Deep Field, but in the radio. And we want to see how many galaxies we can observe in neutral hydrogen emission. We want to push past our knowledge of the local universe and probe back to when the universe was less than a third of its age. So these will be the deepest direct observations of neutral hydrogen ever until the SKA comes online. So we're really excited and terrified for the project to begin. We will start taking data for all these large projects in 2018. So we're waiting for all 64 dishes to be ready and raring to go, and then they'll let us onto it. Why there's this funny vuvuzela shape here is that what I'm trying to illustrate here is the field of view that you observe at different frequencies is different with the same diameter telescope. And as you go to lower frequency, you can actually see a larger patch of sky. And so what I'm trying to illustrate here is that when we look at the universe with the Meerkat telescope, our most distant observations will actually have a larger area that we will look at. And so the shape of the cosmic volume that we'll be looking at is sort of in the shape of a vuvuzela. So it sort of fits the soccer theme. The other big project, which is being led by Prof. Erwin de Blok, who was a professor here at UCT, and he is now an associated professor, he's now back in the Netherlands, is to look at a sample of about 30 nearby galaxies, deeper than anyone has ever looked at them before. So it's like the Things survey that I showed you before, but on steroids. So basically really looking even deeper. So what this is showing you is what they're trying to get at. This is a galaxy which they've observed in neutral hydrogen. This is the optical. And this is when they looked at that same galaxy with much deeper observations with the Westerbork telescope. So this is the kind of thing they want to do. You can really see, if the longer you observe, you can see down to much fainter densities of hydrogen, and really try to learn about the outskirts of galaxies and possibly whether they connect to the cosmic web and how gas gets back into galaxies. So they're looking at star formation and the flow of gas into and out of galaxies. The MIGHTY survey is being led by two researchers. One of them is Professor Russ Taylor in our department, and the other is Matt Jarvis at Oxford. And they will be doing a radio continuum survey, which will also have an H1 component, a neutral hydrogen component. This is actually a picture of another survey, but this is to give you the sort of idea. They'll be looking at a larger patch of sky, and they're interested in studying radio galaxies and the connection between these active galactic nuclei, the supermassive black holes in these galaxies, and the relationship to star formation and other things in these galaxies. They're also very interested in looking at magnetism in galaxies, which you can do with these kinds of observations. And then lastly, Thundercat, which is a survey being led by our head of department, Prof. Patrick Wout, and then Prof. Rob Venter from Oxford. And this survey is rather different. It's not looking at galaxies specifically, it's looking at transients. And transients, as we like to say, are things that go bang or bump in the night. They are not things that stay the same brightness all the time, but they are things that suddenly drastically alter their brightness, like supernovae, for example, or novae, which are white dwarf stars which have accreted material from their neighbor. They accrete enough that it can go thermonuclear on their surfaces, and then they blow it off in a big explosion, and they brighten for a short period of time and then go back to their original brightness. So they're looking at things that change in brightness, and what they also organized is this little telescope, which they've called Meerlicht, Meer Light, which has been designed in the Netherlands and has already been tested and is soon to be shipped to Cape Town. And it will sit at Sutherland and observe exactly the same direction as the Meerkat. Obviously, it'll only be able to observe at night, whereas the Meerkat is a radio telescope and can observe in the day as well. But all the nighttime observations will have the little Meerlicht also looking at the same patch of sky. It will have the same field of view, and so they'll be able to see if something is transient in the radio part of the spectrum, do they see an optical signal as well? And can they identify where that radio signal came from, a particular galaxy or a particular star? So that's also very exciting times ahead. And so I'm just going to leave you with this last beautiful image of the meerkat looking out and wondering what we might find. Thanks very, very much. Thank you very much. Any questions? Yes. So they think that the phase 1 should be up by about 2025. So they'll start building it while we're observing with the meerkat, and they'll be building it around the meerkat. And then once it's ready, Meerkat will actually become part of the SKA itself. So that Meerkat is South Africa's contribution to the SKA. So it'll be sucked into the larger telescope as the core. Yes. The information coming out. Yeah, they're still trying to figure out how they're going to process the SKA. I mean, it's so hectic for Meerkat that they won't be able to store more than 6 months of data, raw data, coming off the meerkat. It means that their hard drives will get full. And then they've said to us as the projects, if you guys want to store the raw data, you're going to have to make a plan and put it somewhere else, because we need to free up that space for more observations. So storage is going to be an issue. Pardon? And then the analysis of it is something that we are preparing for. Yes, you have to think about these things and how we're going to process this data in quite different ways to how it's been done before. Previously, most radio data has been reduced by hand. You know, people run things through a sort of pipeline of each step to put it together in the right way, but there's a lot of human intervention, and with such enormous data sets, we're not going to be able to do that anymore. So there are lots of people. And welcome to the last lecture on the brief tour of the universe, where we're going to end up right back here in the Cape, actually. And so tonight's lecture is entitled From Meerkat to the SKA. And so what I'm going to try and end off with is a little taste of radio astronomy, what sort of objects and processes radio astronomers study, and then take you towards the SKA, the Square Kilometre Array, which will be the most ginormous telescope ever built on the surface of the Earth, and our contribution to that project, the Meerkat Radio Telescope. So just to put, again, things in more context, radio astronomy is actually a very new field of astronomy. It only began back in the 1930s. Carl Jansky was an engineer working for Bell Labs in the USA, and he was tasked with trying to understand sources of interference for shortwave radio communications. And this was his big antenna that he was partly responsible for building. And what he was doing was studying shortwave radio interference, and by mistake, he discovered radio emission from the center of the Milky Way. Until then, nobody had realized that you would get radio emission from space, necessarily, and so this was a really exciting discovery. In honor of Carl Jansky, we have a unit which we call the Jansky, which is the units of flux density that we measure for radio sources. Typically, they're faint sources, and so we talk about them in this convenient unit. Now, if you compare that the first optical telescope, reason is that we need large sizes or apertures to resolve small angular scales on the sky. And this is because of what is called diffraction. Now, when I'm talking about resolving small angular scales, this is what I mean. What we want to be able to do is separate two objects which are close together on the sky and actually be able to see them as separate blobs rather than all merged together and fuzzy and blurry in our images. So this is a nice illustration of what I mean. So in these are both images of the Andromeda Galaxy. This one is at a 5 arcsecond resolution, and this one has a 1 arcsecond resolution. And so in this image, we can see as separate two objects which are separated by an angular distance of 5 arcseconds, whereas in this picture, it's much sharper. We can separate objects that are as close as 1 arcsecond in the image. And you can just see straight away the better resolution. And now, as I alluded to, resolution is limited by this phenomenon called diffraction that you can't escape. And what happens with diffraction is that as a wave passes through an opening, it is bent. And so what happens here is you've got a wave coming in. Imagine you've got a wall, you've got a little opening in your wall. As the wave passes through that opening, the rays are spread out instead of being parallel anymore. And the longer the wavelength, the more this happens. But luckily, you can counteract that by making a bigger opening, because the larger the opening, the less it happens. Now, because radio wavelengths are long wavelength, much longer than the wavelengths of light, when we talk about the wavelengths used for astronomy was put together by Galileo in the early 1600s, optical astronomy was pretty solidly established, but radio astronomy only starting in 1930. It's less than 100 years old. Now, people were very excited by this discovery at the time, but it was unfortunately the time of the Great Depression. There was a radio engineer named Grote Reber who was very excited and wanted to follow up on this discovery. He was also a ham radio operator. Here he is. And he started applying for jobs. He wanted to work at Bell Labs, in fact, and study this in more detail. But unfortunately, because of the budgetary constraints of the time, they were not hiring, and nobody was hiring new astronomers. So he decided, well, to hell with that, I'm going to build my own telescope then. And he did, in his backyard. So he built his own radio antenna. Here's the feed, the receiver, here's the reflecting dish. And he mapped out the Milky Way, and he found emission from other sources in the sky in the direction of the constellation of Cassiopeia and of Cygnus. And he had actually, he studied the radio sky for the rest of his life. He moved to Hawaii, he also moved to Tasmania, and this was his big thing. Now, since then, after the Second World War, radio astronomy, thanks to the technological advances of radar, etc., it made some progress, and the money started coming in, and people could start using it as a real part of astronomy. And since then, we've built many telescopes on the surface of the Earth. The Parkes radio telescope is one of these, steered to track a source as the Earth rotates, but the detector can move a little bit along these cables. Otherwise, it relies on the rotation of the Earth to be able to scan the sky. It was originally constructed actually with a mesh, like a chicken wire surface, but then in the 1970s, it was built in the 1960s, but in the 1970s they resurfaced it with thin metal panels, and that allows it to observe slightly higher frequency radiation. So the winner for the largest radio telescope on Earth at the moment is the FAST telescope, where FAST, F-A-S-T, stands for the 500-meter spherical aperture telescope. This telescope came online at the end of last year. It's in China, and it's got a similar idea to Arecibo. It's also a fixed, enormous dish, half a kilometer from this side to that side. And we're looking forward to seeing what amazing observations are going to start coming out of this telescope. In fact, I'm going to a meeting in India in a couple of weeks' time, where there will be some astronomers coming from China, and we're hoping that they'll be able to give us some fresh new information about what's happening there. So you'll have noticed that radio telescopes are huge. And so why are they so enormous? Well, typically, radio sources are faint, and radio telescopes have to be built as big as possible to collect as much light as possible. So we saw this picture on Monday where we were looking at the buckets. You can think of your telescope as your light bucket, and if you've only got a limited amount of time to collect light, then you want to build your bucket as big as you can. But it's a 64-meter telescope near Sydney, and so it's a 64-meter diameter, and it has this is where the astronomer will sit, over here, and it's famous for being used to track the Apollo 11 signal, the TV signal. And so if anybody's seen that movie, The Dish, this was the Parkes radio telescope that features heavily in that movie with Sam Neill. Yeah, so not only can it track astronomical signals from space, but also human ones. Another very large telescope, the biggest steerable radio telescope we have on the Earth, is the Green Bank telescope that I showed you, I think, on the first lecture, and it's 105 meters in diameter. And it's got this special Gregorian offset design so that it can maximize the collecting area. The other, almost exactly the same size, there's the Effelsberg telescope in Bonn in Germany, and it's also steerable. Here you can see it compared to the size of a car, and so very similar. Now recently, only recently demoted to second largest telescope in the world, is the Arecibo telescope. This telescope is based in Puerto Rico. It's nestled in the mountains. It's not a steerable radio telescope. It's 300 meters in diameter, or 20 acres of area. And it's a very, very sensitive instrument. And it's famous from being in that James Bond movie, GoldenEye. And I think they were running around up here somewhere in the detector. It can't be